It's a great pleasure meeting you all in another video. In this video, let us discuss 2019 Department Model Paper question number 21. Statement number 1 says, a force is needed to keep an object moving, but according to Newton's first law, until an unbalanced force acts on a system, the body at rest remains at rest and body at motion continues its motion. Therefore, when F is equal to 0, the body may be at rest or may be in a uniform motion. Thus, it's clear the statement 1 is wrong. And if you observe this Newton's first law clearly, you must be able to understand that the body tends to resist to the change. This character is known as inertia, and thus this law is also known as the law of inertia. Statement 2 says, when a ball has been thrown, the force exerted by the hand remains on the ball. So let us go through a few examples to understand this concept. First, we have a ball hung in a ceiling using a light string. So if I ask you to mark the forces, you would mark tension downwards on the string, T and mg on the ball, T upward, mg downwards. Now, let us try to mark the forces on the system soon after the string is cut. Then we know there is no any tension on the string. The T acting on the ball upward is the reaction pair of the tension. Therefore, if tension has diminished, then the reaction pair also diminishes at the same time. Thus, the only force acting now is mg. Now, you must be able to understand, soon after the force is removed, there won't be any force remaining on the ball or on the string. They both diminish at the same time. Let's look at another example. A box is placed on a surface, and if I ask you to mark the forces, you would mark the reaction forces and the mg acting downwards. Now, what if I apply a force F to lift the box up? Then there is no more reaction force from the floor or to the floor. The only forces are F and mg. The reaction force that was acting on the box and the floor has diminished all of a sudden. In case of a ball being thrown is also the same. As far as the ball is in contact with the hand, there is a force between the hand and the ball. As soon as the ball leaves the hand, the force due to the hand and the force on the hand by the ball also diminishes all of a sudden. But the problem escalates when you think what makes the ball to move. So, shall we explore? Are you ready? Before moving on to any explanation, let's look at this video. A baseball pitcher throwing a ball. Why did he swing his hand so hard? Cannot we throw a ball without swinging our hands? Come on, let us understand. What makes the motion possible soon after the force is removed? Here I have a box that is initially at rest, and it's being applied by a force of F for a distance of d. Therefore, a work is done on the box. We know during a work, the kinetic energy is gained. So, soon after the force is removed, the kinetic energy on the box still remains. Then, until the kinetic energy is totally lost, the box can continue its motion. We can give the delta kinetic energy by force into distance because that's the work done here. From the equation, you can understand if you give a larger force, there will be a larger kinetic energy at the end. As we have discussed before, these are the action and reaction pairs acting on the hand and the ball when they are in contact. So this is the free body diagram. So if F is greater, then the final kinetic energy also will be greater as our previous discussion. So let us see what makes this F greater. Here we go for a video again to understand the concept better. Let us look at this action from above. How does it seem to be? The swinging action we are discussing about enables to create a massive torque. So what does this torque has to do with throwing? We know torque is the product of force into perpendicular distance. The perpendicular distance is limited. If there is a massive swing, there is a massive torque that will create a massive force on the ball, which enables the ball to get a higher kinetic energy within a short period of time. When the ball is released, the force is no more, but the kinetic energy remains, which enables a motion for the ball. So we have gone through a detailed explanation for statement B. That is wrong. What about statement C? The product of mass into acceleration is not considered as a force. Let us see. What is Newton's second law of motion? It says that The unbalanced force acting on a body is proportional to the rate of change of momentum. Underline the unbalanced force. So it is the resultant force that is proportional to mass into acceleration. For example, let's see if F1 and F2 are equal, we will have resultant force as 0, therefore mass into acceleration is also 0. Yet we have the forces F1 and F2. So mass into acceleration is not a force, it is the resultant force. In an MCQ question, you are supposed to choose the most suitable answer. For statement C, if you consider, as I have explained in the video earlier, you must be able to choose answer number 3. Statement only C is correct. Hope you got a lot of information from this video. Don't forget to share with your friends. Thank you.